Why should PNM be on your mind? There are lots of reasons. I have two great guests that are going to help explain why. Hello, everyone. I'm Brady Volpe, founder of Nimble This and the Volpe Firm. Welcome back. In this informative panel discussion with two industry leaders, we're going to discuss why PNM should be at the top of everyone's mind if you're in the cable industry and concerned about RF impairments. Let me introduce our guests. First up is Jason Rupe, Principal Architect at CableLabs, focusing on PNM, operation tools, and all things reliability. Jason, welcome back to the show. How are you, and where are you broadcasting from?
Hey Brady, I'm great. I'm in Louisville, Colorado at CableLabs right now.
Great, Jason. Good to see you. Also with us
You
today
too.
is Larry Wolcott, Comcast Fellow and Chief P&M Evangelist. Larry, welcome back. How are you, and where are you located?
Hi, Brady. Hi, everybody. Great to be back talking to you about our favorite passion here, PNM, and calling you from Denver, Colorado. It's sunny and warm today. Looking forward to chatting.
Outstanding. We're getting a little rain in Atlanta here today. It's great to be back with you guys and spending a lot of time together. We do a lot of collaboration and meetings, and while we have some lighthearted moments, we are quite productive and we get a lot of great work done. Our contributions to the industry have been, I would say, pretty invaluable, and we develop a lot of reference materials, standards documents, training resources, and even laying the groundwork for the next big thing in P&M. Today, we're going to delve into topics that are familiar to some, but new to many. Before we begin, I kindly ask that you like and subscribe, and feel free to queue up your questions in the live chat or share your thoughts in the comments section below for anything that we're talking about here. So, guys, I thought one topic of interest to kick off the conversation today would be something we call FMECA. Jason, can you help guide us through what FMECA is all about?
Happy to, and very, very glad to. Now, FMECA stands for Failure Modes, Effects, and Criticality Analysis. And it's a tool that we use in the reliability field quite often to really understand what's going on. And if I'm sharing screen here and you can see it here, here's a nice simple example I like to use when introducing this topic. And sometimes you'll see it as failure modes effects analysis, but I like to add the criticality element as this is often done because criticality really is what drives us to do what we do. Now, take a teacup, for example. You've got a teacup. We could refer to that as the system. We would exclude things like the saucer or the contents of the cup and just consider the cup for simplicity's sake. And then we would look at its use cases, such as, well, it's got to insulate a beverage. It's got to prevent spilling. It's got to be portable. You got to be able to access it. It's got to be able to deliver the content. There'd be subsystems perhaps in this, even though we like to think of a teacup as a solid thing. There's a part of it that holds tea. There's a part of it that is for lifting it to the mouth or for pouring. Those are parts of the teacup that are somewhat independent even when it's integrated into a system. So they could be thought of as parts or subsystems. And then you've got the components, the handle, the sides, the bottom, the rim, the lid. So again, while integrated, they are really parts of that function. So then we look at how that system can fail. It can have cracks, it can be warped, it can be broken, discolored. There's all sorts of ways that that teacup can fail to do its job. And then there's all the effects that fall from that. If it breaks, we could have liquid leaking. We could burn the user if it's a hot liquid. We could damage the clothing. We could cut the user if the edge is sharp from the break, so on and so forth. And then we think about, well, what are the most likely of these? What is the impact of these? And how many people are impacted when you do have an impact? And the outcome is a criticality assessment. Now think of a large scale system like we have here that is the communication network and the access side in particular. It gets a lot more complicated than a teacup. And so we as a large group have been working very hard for quite some time to document all of that and to basically figure out the various ways that the access network can fail, and then what does that tell us about?
Very, very cool. So thanks for the overview, Jason. Larry, I know you also have done work on FMECA. Where do you see this taking us?
Brady, this is exciting to me because it's really where the rubber meets the road. We work in, we'll talk about it a little bit more later, but developing the new specifications for proactive network maintenance, like new capabilities within the cable modems or the CMTS, or the RPDs. Then we develop reference software for it, and then really now how do we get it into the field and how do we translate some of this really complex stuff into things that we can use to fix real things that are broken in the cable network. And so it turns out we pretty much know everything that can break and why in our cable network because it's been this way for a long time. And even the new things are pretty similar to the old things like water getting into coaxial cables or amplifier modules failing. We now have this comprehensive failure mode view of this, right? Like water in a coaxial cable or amplifier module failing or incorrect setup and a definition of that that maps it all to a PNM specification, training materials, and how do we assess the criticality, which means how can we prioritize the workforce. And it gives us a kind of a very consistent view of how we run our cable networks and how do we react to failures in that system and how do we prioritize repairs. It's just a really excellent uniform way of keeping track of all these things. Now, FMECA isn't a tool or it isn't a technology. It's more of a methodology or a system that helps us keep track of things and make sure we deal with them consistently. And so to me, the final frontier of PNM is not yet another tool, although there's always a new one, but more so how do we translate that efficiently into repairs and things that mean stuff to our customers, better service, reliability, etc. So I'm very excited. We'll go through some examples later too, as a matter of fact.
Very cool. So, Jason, you've talked about explainability and the different types of failure modes that we've worked through FMECA. Can you elaborate on that a little more?
Yeah, absolutely. And you're right, explainability, that's key. Once we have this understanding, it becomes a reference. So as we do things like create a machine learning model that helps us to identify faults in the network, we have the explainability. So it might be able to identify certain things that we can't see, but we can go back and link that to an understanding, and that helps us know that it's the right choice, right decision to be made. But it also helps us in building a lot of the tools and methodologies. When it comes down to it, PNM in the access network is really about fault management. So as you look at the RF and you look at the impairments that we can identify in terms of those signatures and in terms of those impact on the overall RF signal and the ability for the access network to carry on that service and with high quality, we can translate that now back into what could be happening in the field. That helps us to then identify it, figure out if it's critical, localize the problem, and then know what we got to do about it. And then if we've got to do something about it and where we've got to send them, we know where to send and who to send so that it can be very efficient. So rather than just say, well, we have an echo cavity or we have ingress coming into the network, we've got to send a technician and we just kind of push the technician out the door. Well, we don't need to be like that. We can be very specific. We can use our PNM data and we can use our understanding of the linkage between what we see in the data and the failure modes into those conditions in the outside plant to say, we have a strong understanding that it's somewhere in this part of the network. It's probably as a result, it's probably in this specific part, or look for these particular conditions when you go out there to troubleshoot. You'll find something that looks like this and you'll know exactly where to go. So rather than just say somewhere in the access network or somewhere on this node or beyond this amplifier even, we can say it's down this leg or it's off this tap or it's in this customer's location. That's the real value of PNM, is localizing it so you know what to do. And also we have the resiliency mechanisms that keep us going too. So we've studied the resiliency side of this, which allows us to know, is this urgent? Do we have some time? So do we have resiliency mechanisms out there that can kind of buy us time and let us plan to do this activity correctly? The real value of PNM, and I'm sure everyone knows this, is you've got the time to be able to plan your work accordingly and be efficient with that work to maybe and sometimes solve multiple problems and get it before the network degrades, get it well before service degrades, before the customer even knows there's an issue or can even be impacted by an issue. So we continue to have high reliable service.
Yeah, and I think that planning of work is one of the goals. I don't know if it's, well, one of the important aspects that we find out of PNM, being able to identify, is that problem in home or is it an outside plant? And another thing that we've identified is, stable modems versus intermittent modems. Um, so I don't know if maybe Jason or Larry, if you want to take a stab at discussing the value of being able to identify intermittent modems. Maybe Larry, can you tag that one?
Sure. Yeah. Yeah. Jason and I are working on this time variant component to PNM, which has always been part of the mystery, right? Like, we know that things like adaptive pre-equalization and just forward equalizers and channel bonding are really good at compensating for things in the plant. And we're doing all these great examples of like water in the cable, for example, where a really poorly functioning cable can deliver actually pretty good service and pretty reliable until something happens in the time dimension. Environmentally, like the wind blowing around a loose cable. That's a very time variant scenario. Or the temperature drops and the water in the cable freezes and remarkably restores the cable's functionality to almost perfect sometimes. But it's the time variability component of these measurements that really makes it tricky. So if you send a technician out and the technician is looking for a certain condition and it doesn't happen to be present at that time, that creates all kinds of problems. And also, analyzing, proactively ahead of conditions like freezing temperatures and rain, so that we can use that, environmental connection to the time component to help prioritize. It's fascinating. Really, we know that reliable service is super important to our customers, and it's not just reliable now, but it's reliable over a period of time. And so that's part of the secret sauce that we're working on with PNM.
Awesome. Thanks, Larry. So we've discussed a bit about, some of the details of how FMECA and other failure modes will help us continue to evolve PNM. So we're kind of in the trees. Let's look at the forest and discuss why PNM is becoming increasingly more important to service reliability. Particularly when we look at 10G initiatives, how do we see PNM being used by cable operators to help achieve their 10G goals? Larry, your thoughts on that?
Sure. I mean, PNM is really some of the underpinnings for all of the work that's going on in DOCSIS for tools and technology. Jason will talk a little bit about, some of the working groups that we've started up. But if you think about the way that full duplex DOCSIS or extended spectrum DOCSIS works, it's incredibly important and now required for the operation of the system, so that we've instrumented our cable modems in ways that we can use them as sensors to be an active part, of the orchestration process for turning on signals and tuning the environment so that they work properly. And that's kind of a side effect of PNM, but ongoing, the complexity of our networks is going through the roof, right? With the things like PMA, where we're adapting modulation profiles, that's a very integral part of PNM, because we know when and how we can defer maintenance so that we can optimize our workforce, right? Hey, we don't have to run and fight fires every day now. We can put them in containers, if you will, at the cost of maybe a little bit of capacity. Our customers cannot have to feel it at this moment. And then, we can get out there when it's and work on that network so that it's least impactful for our customers and improves their perception of our service. So it's all about optimizing. Super, super important for DOCSIS 4.0 and where we're going with 10G. It's fundamental to the operation of full duplex, I can say for sure. And just scratching the surface, we're already designing PNM for DOCSIS 4.0. It's starting to show up in some of our tools and technology, and I'm very excited about it. And I'll be honest, without PNM, unpacking a lot of the technical complexity as a human, it's incredibly difficult to interpret how these signals are working now. So it's just super important to running our next generation networks.
Yeah, no, the complexity is definitely there. I think we've all experienced that in the PNM arena, whether or not you're, Jason, you're running a working group trying to herd us all as cats, or whether you're training a cable operator. So, Jason, I would toss this to you. What are your thoughts from, how we're matching PNM to 10G initiatives? I know you also are involved in working groups.
Yep.
Go ahead, your thoughts on that.
Yeah, I actually want to share some high-level things and then show a couple of screenshots as well of a couple slides that kind of will bring a point home. We work on this concept that Larry came up with, PNM DevOps, where we focus one working group on the tools and the technology and kind of what we refer to as the science side of proactive network maintenance. And then we carry a lot of that forward into impacting the field forces so that they know how to do their job best. And that's kind of done with two working groups where we do coordination hand in hand. But beyond that, there's other working groups that impact here as well. And we run that kind of with a handoff and as kind of a community as well, where we have DOCSIS 4.0 tools and readiness, where we're developing all the techniques and the capabilities and making sure the tools are there. That's another working group we have over at SCT side. And then there is also one that we are developing the cable version of how we are going to assure network and service reliability. And we're viewing service reliability as all the aspects of making sure that when I want to use an access network service, a DOCSIS-based service, the cable providers are providing, that it is highly reliable, meaning when I try to stream a service, I don't have anything happen that's out of the ordinary, which means I've got enough bandwidth, the latency's where I need it to be, that I've got reliability there as well, and all those aspects are going to be reflected in that. Now, PNM is really focused on proactive network maintenance, so that's maintenance and trying to stay ahead of the problem, so making it proactive. And most of our operators out there, and most of the operators in the world, really have a program in place. Now, some might be always questioning and wavering, as I often get questions, or I have conversations with some operators, and they'll tell me that they work really hard to try to get ahead of the load of work, but so often they're in reaction mode and they don't have the effort to push forward. A couple years back, I did some analysis that says, well, if you're in that world, is it worth really pushing ahead and getting into that? And I really wanted to check our facts on this. So I did some analysis, and hopefully you can see my screen here there. I'm not going to explain all this because it's a ton here. I just want you to see that built some state models and used some Markov analysis and actually ran thousands of scenarios of different combinations of parameters, like if my cost is like this, if I'm this good at doing maintenance, running thousands of these possible combinations for every reasonable operations that an operator might have, and we're looking at various different plants and different conditions. I built a model that I analyzed and did a lot of work with. And what we found in this model is making some assumptions like if I do proactive and reactive maintenance, or if I just do reactive maintenance and only about half of, let's say half of my proactive stuff would have turned into a maintenance. So that means half my proactive work is just really wasted. I'm going out there looking and chasing ghosts or chasing problems that aren't there. In that case, my availability is massively better when I'm doing proactive, even if half of those are wasting my time. Likewise, the cost is actually still significantly lower overall by doing proactive maintenance on top of reactive maintenance, even in a very poor condition case. And that was true over all sorts of states of degradation in my network. And then looking at all those degradation states, sometimes that difference is small. Like if my network is really, really tight and really new and good, and I don't have a lot of proactive problems, I still want to do proactive network maintenance. I'm still going to occasionally find an issue that I can solve before it impacts a customer. It's still worth doing. But even as my network gets degraded, it becomes much more important to do that. And looking over time, you see all sorts of that cost difference is always positive, meaning I'm never going to lose money by doing proactive network maintenance. It's always the right thing to do in any reasonable condition. And for that reason, it's a no-brainer, honestly. And so if you're kind of looking at your actions, it's always useful as a network operator to look and say, am I doing enough PNM? Am I doing the right amount of PNM? And you want to kind of push your limits there. You want to push to a point where most of your efforts going toward the proactive side, so that you're well ahead of those customer problems. Now, you're always going to have a cable cut. You're always going to have a power outage that ends up causing other issues. So you can't stay ahead of everything, but where you can, you want to be ahead, and you want to make sure and do that work. And that's the mindset, and that's the mentality that everyone's got to have.
Yeah, that's a lot of good information that you just provided, Jason. I think it's really important for our viewers to see some of this information if they haven't kind of seen all the work that goes behind PNM. It's not just like, we build a tool and say, try this and see how it works. There's so much research that goes on behind the scenes, whether it's by CableLabs or by a lot of the great work that Larry and his team that does. There's a lot that goes on behind there, and so I think to expand upon that is, if you have PNM, you really have to apply PNM to get the benefits out of it, and that's the important aspect of that. Larry, anything you want to add on to that?
I love that. That was such a great deck, Jason, and it really illustrates our relationship. We talk about internally, we say art and science working together, and that's how we work our working groups, right? Jason just talked about the science of PNM and why proactive is important from a business perspective. It makes tons of sense, and I love that you said basically, if you read the charts, you can't be proactive enough, from a business benefit, right? It's the gift that keeps on giving. But from an operational perspective, it's super intuitive to us. If you've been doing this for a long time, you don't wait for things to break, especially if you can see them breaking before they do, because it's a lot easier to fix these things on your terms when you can be more surgical and precise about them, like in maintenance windows and working with customers, rather than having them go through the experience of an outage and then a call in the middle of the night to get a technician out there and just all of that. Um, I love the view, Jason. I really appreciate that you shared that with our audience. And sometimes, in fairness to Brady's comment, sometimes we do just put a new tool out there and say, hey, what does this do for us? But that's a different part of the process. There is a lot more that goes into it. And we don't just do things because they're technically interesting. They have to really be meaningful to our customers and our business. So that's a really great view, Jason.
Too true. Too
And
true.
I'll just add, if I can add, we are customer focused. All of us, we have a great community. We're always working together. And it's not like, hey, CableLabs is going to do this and Comcast is going to do this and Brady's company is going to do this. We work together. We share the knowledge. We say, now, what does this tell us? We ask ourselves, how can I take this forward and make this useful to everyone? We share because we are very customer focused at the end of the day. We want to figure out how to make DOCSIS and access networks the best for customers. It helps operators to reduce costs. It helps the tool vendors to be able to provide that capability to operators, and it definitely helps customers. It's part of our vision for 10G. Reliability is one of those 4 pillars. PNM is the anchor of that pillar, and we remain focused on that.
Yeah, I think it's really impressive how all of us collaborate together, right? Whether we're competitors or not competitors, we really have a transparent approach to everything, and I think that truly benefits the industry. So I'm really pleased with how that works, and I think CableLabs is a critical asset to bringing us all together and providing that collaboration. So that's exciting.
Yeah. So think about before we leave on that one. Let me put an exclamation mark on Brady's comment. Like, think about industrially, we have CableLabs and SCTE as tools to us to collaborate together, and PNM is a crazy good example of that, where we have people who compete, vendors, operators. We all have this common language called PNM, and all the meaning of that and what it means to us individually in our roles in the cable ecosystem is standard, right? And that's only because we have PNM and CableLabs and SCTE working together, in this consortium. It's pretty cool that I can say in-channel frequency response or impulse, echo, and we all know what that means and why that's important or not. So it's a really unique thing for us.
Yeah, and to that, I mean, Larry, you have really been leading the charge on the PNM front in so many different ways, but it still
Yes.
seems like there's so much more work to do. We keep learning more. So, with that being said, what has been keeping you busy, Larry? What kind of new things have you been working on?
That's a great segue, Brady. Let me bring up a little bit of a deck I brought to share with everybody.
Awesome.
And this is things that we're working on collectively. Jason and I, Brady, you're involved in this too, so it won't be a surprise to you. But I'm going to take you through this. Is the deck okay?
Yes, sir. It looks
All
great.
right. Well, PNM is old yet new, and it's the gift that keeps on giving. So as we, at Comcast, we're doing all of these system upgrades into, higher frequency spectrum for upstreams. We're going into symmetric multi-gig systems on or service on the same old coaxial cable. And, it turns out the tools that we have been using all along are starting to manifest new and really super important discoveries for that effort. So I'm going to take you through a couple of examples of that, and then some things that Jason and I are working on in the specification space that you're going to start to see showing up in the new tools and why you care about that. So that's pretty exciting. In this case, we're working on Network Operations Subcommittee number 7. All of 3 of us are actively involved in this. Using our full band spectrum for full band capture spectrum analyzers. These are basically spectrum analyzers embedded within the cable modems to do a new kind of analysis to show us an old problem that we frankly just, I don't want to say missed, but it wasn't our primary focus because we have had other ways of detecting them, but not in the way that we need to detect them today. So this is kind of exciting. In this example, because we're starting to do mid-split upgrades, meaning extending the upstream spectrum to get more upstream service to our customers, we're occasionally encountering these edge cases where a system amplifier, will have an incorrect setup, and the result of that is that once we add additional RF power to this channel lineup, it results in a nonlinear effect, and distortion noise increases, causing the modems to go offline, right? So think about that. There's a physical condition in our network that works fine today, but once we activate additional spectrum, it can potentially damage the service, right? And this is okay because the system the service that we're offering today works fine, but now we can see proactively before we activate that additional RF spectrum where and what to do about it, right? That's the crux of PNM. Jason or Brady, do you guys want to talk to this slide a little bit? I'll take you through the details.
So what you're looking at here, Larry, is full band capture signals. We're using DOCSIS 3.0 or 3.1 modems to see all the RF signals in the subscriber's home, right? And you're pointing at an amplifier. So one of these signals looks like it's having problems. The one that you have circled, it looks like there's some noise in the unoccupied spectrum, the spectrum where we do not have RF channels. Is that a correct statement?
You got it. So I'm going to take you through the next slide. So here's what we discovered when we got there. This RF spectrum here on the right is measured by a signal meter. And here you can see the confirmation basically at the output of this amplifier. By the way, it wasn't at the input of the amplifier, so there's another clue. And that was kind of what the previous picture showed you. This noise here in the vacant spectrum is not supposed to be there. And that's actually a product, that's the output of the amplifier being caused by an incorrect setup within the amplifier. And that setup is actually controlled by manually configuring pads and equalizers at important places within the gain stages of the amplifier. And here's a picture of what that looked like. It started off with a 0 equalizer, a 12 pad on the input, and a 0 mid stage, and then you can see the return pad at 0 and 8 on the inputs and outputs respectively. Now this is network maintenance techs will know exactly what this is, but what this means is basically a whole lot of power coming in on the front end of this amplifier, and what's happening is it's kind of like if Brady, you had a good metaphor for this about plugging your iPod into your car radio. Explain that.
So yeah, so I mean, you're basically overdriving um, your stereo if you have too much signal on the input, and that's going to cause distortion. So you have too much signal in to a radio, too much distortion.
You got it. And so what you're
Oh, we may have
impact
there we go.
distortion caused by an overdriving amplifier. So now, lo and behold, using this technology that's been here and serving us well for 10 years, we have a new way of measuring something old that's really important to us today that it's not that we didn't care about before, it just didn't have the same meaning. So this is pretty exciting. Now, this is the after slide. You can see where the padding um, increased dramatically to a 19 forward pad with a 3 equalizer, and now we have a 5 mid-stage pad. And then, of course, a pretty dramatic change. This is a little wacky, but 2 input pad on the return and 25 on the output. It's pretty significant. But if you take a look at the distortion products coming out of the amplifier, readily available from all of those customer equipment located beyond this amplifier, clearly you can see that distortion noise. And by the way, the MER, the performance of the active spectrum dramatically improved as well. So this is good news. Now that when we activate additional spectrum on this customer on these customers in this node, they won't fall off the cliff, and we have proactively saved the day yet again.
Yeah, and this is awesome, right? Because what this is giving us the ability to do is determine if we have distortion in our plants, which is obviously going to cause both video and data problems for customers, or can potentially do that, may not cause it. But this could happen because I think in the example you shown, we had a technician maybe improperly balance an RF amplifier, or it could happen maybe not because the amplifier is improperly balanced, but just as you said, Larry, we start to add more and more channels in our downstream. We start to add more OFDM channels in our downstream. And then if we don't go back and realign our amplifier, these distortion products are going to happen anyhow and then start to impact our subscribers.
You got it, spot on. And in fairness, these techs knew exactly what to do when we got there. This node was recently converted, and there were some plant changes where they cut out a directional coupler, and there were some other things. The plant changed, but this amplifier was hidden behind a fence in a bush behind a subscriber's yard, and it just got missed. And that happens occasionally, right? So it's not so much tech didn't know what they were doing, more so, wow, we have a lot of things going on, and we really need to use PMA to help automate, and help us humans find things that are hidden in bushes. Is just one of many examples of that. Now, what I have here, this is actually the output before and after from that same customer's house. And here you can see, and this is a full band capture spectrum trace that all of you on this call and familiar with this have available at your disposal. You can clearly see the total power. This is dBmV total power basically at the cable modem is 31. It goes down to 18.9, and that's very consistent with the additional padding that the technician put on the front end of that amplifier. So that's linear. But when you hear the term nonlinear, that's what distortion is all about. The reason that's so important is here you can see by adding 12 dB of pad, we actually lose 12 dB of signal. This is counterintuitive, but it's super important in the crux of this whole thing. We're losing 12 dB of signal. It's going down, but we're gaining 12 or 27 dB of noise rejection. Well, actually, we're losing 27 dB of distortion noise coming out of the amplifier. So if you look at the ratio, that's nonlinear. It's not 12 dB of signal and 12 dB of noise. The reason that this is so important, folks, this is it in a nutshell, is if we add another couple of dB of RF spectrum by adding another OFDM channel here, that isn't 2 or 3 dB of noise, it's adding 6 or 10 dB of noise because it's nonlinear distortion. So that's why the customers, if they're really close to that threshold of operation on the MER, you add a little extra power, you're adding a lot of extra noise, and it can't come back online. So what a great opportunity for PNM.
And I think that point that you're making
Absolutely.
is so important for people to understand. A lot of times, just like intuitively, you think more signal level into the modem is better, more signal throughout the plant is better, and it's not. It's because you get, it's not a 1-to-1 ratio. It's like 1 dB of more signal does not give you 1 dB of more distortion. 1 dB of more signal might give you 2 or even 3 dB of more distortion. And that's something we all have to keep in mind as if we're technicians in the field, that more is not better.
Unless it's PNM.
Unless it's PNM.
Okay. Are we good? Anything else on this, or I can shift gears to the
Go ahead, shift gears.
OFDMA discussion?
Yeah,
Okay.
Larry, that amplifier that you were talking about in that cramped space, yeah, you know what you call those, right?
Oh
No,
no.
It's a
Jason.
cramplifier.
I
It's a
knew it was
cramplifier.
coming.
Oh boy.
Yep.
All right.
You are
So
the
this
king
is
of bad jokes.
what we put up with in our working groups. So I'm going to take you on the next little PNM adventure. We have OFDMA for all of those of you who are doing mid splits and high splits and all of this great stuff around the world. You're in the thick. So it turns out that because we are going to OFDMA from SC-QAM, the opportunities and challenges change a little bit. Now, they're still super valuable. They just have different meaning. And the reason for that is because these SC-QAM channels are more narrow, and not only are they more narrow, we don't actually use the full contiguous occupied spectrum for PNM. We actually have channel gaps in there. And here, this visualization on the left, you can depicts that. We're actually, for example, on a 6.4 megahertz SC-QAM channel, we only have fully instrumented about 5.12 megasymbols of that channel. That's a 0.8 alpha of the SC-QAM spectrum. That's just how our spec works. So we're only equalizing 5.12 megasymbol bandwidth of that full 6.4. So if you actually look at this example where we have 20.48 megahertz of total occupied spectrum, there's a bunch in there that we can't actually use for PNM. So that's one part. And then the other thing is the resolution of that analysis is quite a bit smaller. It's, if you do the math, we have it documented in a bunch of our stuff here with a 24 tap equalizer coefficient. That's only 244 kilohertz resolution of that part of the spectrum. Now, the second you drop in OFDMA, on a 25.6 megahertz total occupied spectrum, this is just an example, at 50 or even 25 kilohertz subcarrier spacing, you got a heck of a lot more, twice as much, or even, quadruple as many measurement points. So the resolution is more accurate, and it's contiguous, meaning you can see the entire spectrum. And today we have to compensate for that by, sometimes you'll see us all in the different tools stitching the equalizer coefficients in a quasi-contiguous way, but it's okay, but it's not great. And so that's why we're kind of revisiting how we interpret and present some of these metrics. For example, in-channel frequency response. Brady, give me your perspective about in-channel frequency response and why it's important to us.
Well, ICFR, in-channel frequency response, gives us basically the inverse of what the CMTS is seeing. So it's telling us how the cable modem is pre-distorting its output when it transmits that signal to the CMTS and compensates for any impairments between the cable modem and the CMTS. That's a short version of ICFR.
That's it, spot on. And it's become incredibly valuable, and in fact, arguably the most important PNM metric that you can use, fundamentally to assert the health of that channel. But the meaning changes because, think about this, we go from a 5.12 megasymbol bandwidth to 20, 30, 40 megahertz wide. So now all of a sudden, what used to be a tilt is actually part of a sine wave, right? Now you can see the whole thing, so you have a different perspective. You're stepping back from it, you can see more of it. And before, what used to be ICFR of 4 is actually part of a really big tilt. Like the difference between and I did this intentionally, these top two graphs have an ICFR of 3.6. Meh. Now, the difference between what we're seeing in these top two graphs is incredibly important. One is tilt caused by a system, and one is a standing wave caused by a reflection cavity, and that's a drop. So one is on a customer premise, one's on the network, and they're both very common. So not just ICFR, what we're doing is introducing tilt. And it's incredibly easy to do because most folks who do a little bit of math know what a regression is. You basically take all of the points of that frequency response and you put them into a linear regression. It's a least squares routine, and you can draw a line across that. And it's basically a trend line. And this is exactly what our field meters do to calculate tilt. So now, in this case, we have a tilt of 3.8 versus a tilt of 2.3. So now we're starting to be able to distinguish an actual system tilt versus a standing wave frequency response. And likewise for a singular reflection that has a different meaning, or actually that's a filter response. So channel tilt is coming, very easy but very useful and meaningful for troubleshooting and helping us directionally decide where to go to troubleshoot. And this one I love. We actually got it out of the 3.1 specification and turned it into something a little bit more meaningful. It's the channel tilt residual. Now, you don't want to say that 5 times really fast because it will sound like mumbo jumbo to you, but I will tell you that the reason we care about this is for the machines, the features that our machine learning and our AI routines can use to determine if it's this versus that. It's a feature that allows us to determine, if you think about an ICFR of 3.6 on these top two graphs, one has a tilt residual of 0.9, which is very small. One has a tilt residual of 2.6, which is very large. So now you have enough metrics to say this is a system tilt problem, or this is probably an individual drop problem. If you see where we're going with the theme here.
Absolutely.
Yep. Now, more on the tilt. So we have tilt residual, and ripple period. We have this kind of in our existing tools, but the resolution is pretty small when you're staring at a 5.12 megasymbol bandwidth. We call them ripples or periods, or what do you call ripples in your tool, Brady?
Ripples.
Ripples. There you go.
And I just wanted to comment on that because you mentioned the resolution when you have our legacy SC QAM is smaller than what we have with OFDM channels. And that's because we have more samples in an OFDM channel, right, Larry?
Well, to be technically correct, it's larger. It's a 244 kilohertz resolution bandwidth, whereas this is 25 or 50 kilohertz. So it's much higher resolution bandwidth, but it's actually less resolution. So just a semantic quibble about smaller.
Thank you for clarifying.
You got it. But in this case, so if you have a ripple period, now your tools can start to translate this into feet, which we're accustomed to with upstream equalizers, except for, think about the resolution. 33.91 feet is going to be within inches, whereas Brady, at a 24 tap equalizer, what's the distance limitation generally that we're used to?
We're generally plus or minus 25 feet as the best that we can get to.
The best you can get to is 25 feet, and now we're going to be 25 inches. So it's incredibly good in terms of accuracy. So I'm very excited about that. And that's why we're adding this ripple period, basic velocity of propagation math. If you know the type of cable, etc., you can very easily use this ripple period to calculate distance. So that's always useful for our technicians. Okay, so we have tilt residual, ripple period, and this is not new, but signature matching in OFDMA works a little bit differently because the equalization coefficients are frequency domain versus time domain, and some other reasons why it works differently. But it still works. It's just as good, but even more accurate, again, because the resolution's higher. And incredibly precise resolution with these OFDMA equalizers. You can start to see very, very tiny little ripples in there. Not that the size of the ripple matters so much as the fact that one exists at all is going to be very important going into the future. And Lastly, and this one is going to be worthy of a minute or two. I'm going to do a time check here. We've got about 15 minutes left. Is transmitter headroom. And maybe we should have put this one up front. Jason, key us up on this one and what your thoughts are.
Yeah, so Larry's given kind of four measurements, and if you think of how those measurements are, we get data from the network, and the first thing we do is we kind of level set with a slope. We look at the overall range. That range is important. Then we level set to remove a slope. Then we look at the residuals after removal of the slope, and then what we have is kind of that signal that remains. And now we're going to look at the headroom, meaning how much resource do we have left to deal with this from an energy perspective. So if we give more energy to the system, will that allow us to continue to have resiliency of the service? Or is there not enough room to give it more energy? That's in a nutshell what Larry's describing with this new measurement of headroom. Now, it's a pretty complicated issue because it's a complex system. It's what us in the math world call a dynamical system, because you have an input and you've got sort of a recurrence back of an output, and then it affects the input. And so you really don't know how the system's going to behave unless you understand exactly how it is. And that's when we get into things like, do we need a digital twin to understand how this behaves? Well, we have these systems and we're working with them live. So the thing to do is to make adjustments we know are best and then to see what happens. So we're considering that there is headspace left in the cable modem. There is maybe some energy headspace left in the CMTS. And we're going to try to come up with some math models that help us understand, given a given performance, how much resiliency or how much left do we have in those resiliency mechanisms, or are we pushing near the limits? Because that's going to help us understand whether or not this is an urgent matter or not. And the other thing that Larry has described in here that is kind of left and not described yet is, if you think back what we talked about early in this presentation, variability in the plant. Now, the plant is not built to be variable. So if we have a certain amount of variability in the plant, which becomes significant, sometimes we need more, say, echo cancellation, or need a little more energy in this way. Or sometimes we end up pushing it too much and we get clipping if we push it too far. And it's going to be changes in the network that could lead us to these poor conditions. And so if I've got a highly variable network, that points to some sort of degradation. Either something is broken and now the wind movement is causing issues, or we've got water getting into cable or even into an amplifier. And by the way, that's called a damplifier when the amplifier is wet. But but you can have these conditions out there and they all point to plant variability. And the idea is, if I can see the variability, I want to go after it. So each of these measurements that Larry's describing, we want to look at that over time and look at the variability of each of those parameters as well to understand, is this an issue that is urgent because I think it's fine now, but occasionally it gets worse. And if the weather gets bad, I may see a very bad condition. That makes it very urgent, even if it doesn't look urgent today, as opposed to one that's maybe very stable and a little worse. We might actually say that's more stable and I can plan on doing it later. So figuring out what's most urgent and that criticality part of FMECA comes back in here. Which ones are the most critical for us to go after? And that's what we need to keep our eye on here. And we're building this whole system set of tools to allow us to make good decisions and optimize our use of our energy here.
So Jason, you need your own stand-up show. You managed to tie FMECA back into this, and Larry, you're gonna show us that calculating cable modem transmit power is really, really complicated.
It is. And so this is actually a screenshot. Maybe I'll take you through the live one. I'll talk through this, and I'll make it quick here. But this is why we're not. The tools have an opportunity, and we're learning this as we start to add an OFDMA channel or two. Things start to behave in a way that we're not used to seeing, right? And what is the meaning of maximum transmit and equalization playing a role into that, and how much? And at what point are we going to run out and start to see, insufficient energy hitting the CMTS? So that's the point of this whole thing. And when it gets so complicated, and especially we haven't, from the specification perspective, it's tricky. Let me take you through this. We call them legacy channels, or these are standard SC-QAM channels. And let's say hypothetically we have 4 of them and 1 OFDMA channel. In the spreadsheet, we modeled it so you can have up to 6 legacy channels and 2 OFDMA channels. But remember, it's definable, but generally 65 dBmV is our maximum transmit power that we have to work with. And this is across the entire transmit channel set. That's all of the channels participating in the upstream conversation. So if you add a channel or take away a channel, that actually increases or decreases your maximum transmit level. Because the reason for that is we can't have any individual cable modem talking louder than 65, right? That's our ceiling. And so how do you actually calculate those? It gets so tricky because first of all, these legacy channels, it depends on your bandwidth of the channel, because we have to calculate the power spectral density, of that channel, and we report it in power 6.4, which is 6.4 megahertz of spectrum. So that's, basically what is the power spectral density that we're reporting. Now, just because we just couldn't keep it simple, the OFDMA channel power reporting is power 1.6, meaning we slice it into 1.6 power equivalent and report that power. So the power equivalent between 1.6 and 6.4 is about 6.01 dB. So that'll give you a sense about how we have to translate from one power to another before we sum them all and get to 65 dBmV. So there's a whole bunch of interesting stuff. You have to add up all the bandwidth and then slice it by 1.6 with a ceiling of 1 to make sure in case you had odd sizes like 800 kilohertz. And it's pretty gnarly. So we go through all of that. And then we basically calculate all of the occupied spectrum that we have in the transmit channel set. That's all of the channels put together, divided by 1.6 megahertz. And then we calculate that ratio of power relative to 65 dBmV. And so that's how we derive the max transmit for any given channel. And here you can see this is an example where we're actually at max transmit. And in this case, because we have 4 6.4 megahertz wide channels and 1 that is 45.6 wide, here's how all of we dynamically calculate all of the max transmits and subtract the total transmit value of the TCP from that transmit channel set. And we can see we're actually at a power deficit of 0.01. So we're running negative headroom. That's it, we're out of gas. So at this point, now we're able to say individually, each channel has a maximum transmit and how much headroom there is. But wait, it gets even more complicated when we start to talk about adaptive pre-equalization. The pre-equalizers in the SC-QAMs come at an expense of transmit power. It's for every, this is not super scientific, but you can think for every dB of ICFR correction you need within the channel, channel fidelity you need to correct for with the equalizer, that costs you about a dB of transmit power. So now we have to add that equalization in here, but it doesn't work the same way for OFDMA because we're normalized to a unity of 1. So in the case of OFDMA, the frequency response doesn't affect the transmit power, but in the case of the SC-QAM, it does. So again, more complexity into the calculations. But the point of all of this is to have a very clean way of measuring, well, your cable modem is pretty close to running out of transmitter headroom or not, because we can't really do that in a very clean and crisp way right now. And if so, is it a linear impairment, meaning the pre-equalizers are compensating for something, or is it just plain, return attenuation that we have to deal with? So again, a lot of complexity here. I'm very excited that we're finding a nice, simple way to put it into something actionable for our field folks. And another problem you're going to have as you add additional OFDMA channels is if you're close to the maximum transmit for the entire channel set, if you add an OFDMA channel, you're either going to be power starved at the CMTS, or you're going to have to reduce your CMTS's commanded nominal receive power. Whole lot to unpack there, but just know that this is next frontier. So I'll stop there.
No, that's awesome, Larry. And if anyone watching, if your head just kind of went boom, um, that's okay. That happens. It's so. I mean, we covered this in a previous show where we kind of touched on modem transmit power, and we used some of the basic information that comes out of the DOCSIS specification, but Larry's sort of taking this to the next level and really getting into the nitty details to make sure we're covering all the aspects of how modem transmit power works. But this is the kind of detail work that the three of us and a larger group of people work on in part of our working groups. And it is some fun that we have when we get in there. And then there's also some challenges when we're trying to work through these problems. So it's exciting and it's fun to be in part of these working groups. So I definitely encourage anyone, if you're watching this and you say this is interesting things, join on the working groups. You'll learn a lot and you'll have a lot of fun participating on it. So thank you so much, Larry. Thank you so much, Jason, for your time. This was a really great conversation that we have. Are there any upcoming events or anything that you guys want to promote?
You want to go first, Larry, or should I?
Oh, go ahead, Jason.
Okay. There's a whole lot of things going on, honestly. We have, if you're an operator, you probably have had a chance to register for an upcoming webinar in PNM that's specific for CableLabs operators. But more importantly, we have a face-to-face coming where we're going to go through some vendor demos and then some operator demos where everyone's going to share what's new and greatest in their capabilities and where their thinking is and what are their challenges. We're going to work through our FMECA in specifics at that event. And that's going to help us a lot because we're going to kind of give it a good look as to where's the next frontier with PNM, where do we got to focus. And also we're going to spend some of our time preparing our, what so far we used to call our primer for best practices, but it's not a primer at all. It's very much a tome on the best practices around PNM. We have one version of that's going to come out here either today or early next week. And then we're going to set our sights on a version 5 that we're going to complete and work through during that face-to-face. And then we're going to set our sights on some bigger things where we're going to pull together all the knowledge in the 3.0 world as well into one reference document for how to do PNM, and then a pocket primer, if you will, for those who just need kind of the brief version without the full deep understanding. So a lot of big plans and a lot of things happening in the near term if you're involved in PNM. If you're a vendor or an operator in the community, jump in and join. We've got the PNM working group at CableLabs. We've got working group 7, Larry runs that. We've got working group 8 in SCT that's focused on service and network reliability. And working group 5 is focused on DOCSIS 4.0 readiness. Larry's example he just shared is a great example of how we do this analysis as a group, and then from that we gain a lot of traction out of it. So it's going to help us in PNM to understand how do we measure how close we are to urgency with addressing a PNM problem. But as Larry pointed out also, this tells us something about if I add an OFDMA channel, which is something we will do as we move into higher splits and we look at DOCSIS 4.0, that this tool becomes relevant for that as well. So we now have some new tools that we can think about making use of to help us to get ready for DOCSIS 4.0. So when we cut over from 3.1 to 4.0 and we offer that new level of service to the customer, they transition without an impact. They can transition and get a higher level of service without any outages, without any issues, without even a hiccup in their service, which is exactly what our goals are.
Yep. Looking forward to the event. I would definitely be there, Jason. Larry, anything you want to promote?
I'll just one big plug here. The SCTE call for papers for Expo 2023, which is in my hometown, Denver, this year. Hopefully, I look forward to seeing all of you and catching up. The call for papers is coming soon, so keep your eyes peeled for that. And we'd love to see PNM related material come into there, and it's always gets good airplay and participation. So if you got anything to write about or want to participate, please do. Looking forward to that.
All right. Thank you, guys. Again, thank you so much, Jason, Larry, and thank you to our listeners. John Downey and I will be back on Friday, February 24th for episode 89 for a Did You Know episode on our DOCSIS live stream with it will be full of questions and answers on DOCSIS, so put it on your calendars and don't miss it. Thanks for watching, everyone, and be sure to drop your comments below. Thanks and so long.
Bye-bye.